Okay, hi everybody. In the last video, we talked about exact functions. So if I have some total differential written as follows, exact differentials are ones for which this definition holds. Right? The cross derivatives are equal. And it's relevant because state variables in thermodynamics are described by exact differentials. Path variables are not. Today we're going to flesh this out a little bit more and use it to derive something called Maxwell Relations. So away we go. This is the first law of thermodynamics. It's written in differential form. du equals dq plus dw. I'm going to solve for dq and dw in terms of state variables. So I can use the definition of entropy. I can use the definition of work. And if I solve those for dq and dw and plug them in, you get something which looks like this. du equals TdS minus PdV. A quick note, some of you may be wondering where did the reversible part go? And I will just tell you briefly that I eliminated them using a trick with inexact differentials. Effectively, they sort of balance one another out. See details in Atkins 3E if you want to figure out how this works. But trust me that this is an equivalent statement of the first law of thermodynamics. This is really important. I was taught that it was called a natural equation. Atkins calls it a fundamental equation. And it's important because it arises from the laws of thermodynamics. Right? I started here, dq plus dw. I did some substitutions, and I end up here. Most important is it suggests that u is a function of specific variables. This is a total differential, and it suggests that u is a function of the variables s and v. These variables, we call them natural variables. Right? So the natural variables of u are entropy and volume. And it will turn out that for each of our four major thermodynamic state variables, internal energy, enthalpy, Helmholtz energy, and Gibbs energy, there is a natural equation and a set of natural variables. I've written them all out here. I'll ask you to do one of them on the homework, and I'll give you some practice with it. But looking at all of these things, you can see they're closely related, right? So U is a function of entropy and volume. Enthalpy is a function of entropy and pressure. Gibbs energy is temperature and pressure. And you might wonder, are there ways to sort of connect some of these things? They all look like permutations, and can I connect them in some way? And in fact, there is. So if I'm going to look at the equation for U, if I know from the natural equation that U is a function of entropy and volume. My mouse pad just died. Give me a second. Let me see if it works. There we go. U equals U of S and V. I can use this expression to write a total differential for U. That is du equals the partial of S. Whoops. This should be the partial of U, sorry. With respect to S at constant V times ds plus the partial of U with respect to V at constant S dV. Again, this just comes from a definition. This is what I mean by a total differential, and I can write it once I define the variables associated with my function. I then look at this expression for the total differential, and I compare it with the natural equation. And what you can see is that the partial of U with respect to S at constant V is equal to temperature. This quantity here is equivalent to this. Similarly, the partial of U with respect to V at constant S is equal to minus P. Now this has some value, and I will talk about that a little bit later. This result by itself has value, and I'll talk about that later. But I can go even a step further. And that is that I know U is a state function. The internal energy is a state function. State functions are exact differentials. Therefore, the cross derivatives are equal. Here, I took a derivative with respect to S, V constant. Here, I did V, S constant. But if I take the cross derivatives, that will tell me that the partial of T with respect to V at constant S, again, I'm differentiating this function with respect to the flip of these two variables, is equal to the partial of P with respect to S at constant V. And this is the primary result. Right? This allows me to connect those four variables that I saw in the natural variables of my thermodynamic functions. So this is an example of a Maxwell relation. It is an unexpected mathematical relationship among partial derivatives arising from the laws of thermodynamics. And this is probably a little bit before your time, but maybe if you watched late night TV before Netflix, you would have seen this guy. His name's Ron Popeil. He was famous for selling you knives and Vegematic and things like this. And this was always a sales pitch, you know, the knives are worth $380, but today only he's going to make it 4 easy payments of, excuse me, $40. He's going to get you even a better deal than that. If you call him the next hour, he'll give it to you for $30. And then he would really put the hook into you, and he would always end with this. He'd say, but wait, there's more. Right? Throw in a free set of Tupperware or something like that. Well, wait, there's more than this. Right? It turns out that each one of these thermodynamic variables gives rise to its own Maxwell relation. You do the exact same thing that you did for the internal energy, right? And you can derive these 4 Maxwell relations. Okay. Why in the world do you possibly care about this? Well, I think there are 2 reasons. The first is that you can use Maxwell relations to make qualitative predictions about how thermodynamic variables change. So here's a kind of question we might ask. How does the internal energy change for some gas expansion at constant entropy? Does it increase, decrease, or stay the same? Note, this is a really, really general type of question. Right? I've just said any gas expansion. I haven't specified ideal or whatever. Well, if I go back and look at one of the results from this Maxwell relationship, it describes how the internal energy changes with volume at constant entropy. This is exactly what I was wondering about. And what this tells me is that it's negative P. Pressure is always a positive quantity. So the right-hand side of this is always going to be negative. And what that means is that the internal energy always decreases when a gas expands at constant volume. And I suggest to you that this might make sense. Constant entropy means delta S is equal to 0, which sounds a lot like an adiabatic expansion, right? When we say constant entropy, we're talking about adiabatic expansions. And in adiabatic expansions, the system does work, it absorbs no heat, energy goes down, right? And this always happens regardless of the identity of the gas. So we can use it to make qualitative predictions. You can also use it to make quantitative predictions. And here's a quick example, right? Use a Maxwell relation to derive an equation for the entropy change of an isothermal expansion of an ideal gas. Here's how you might think about this. So the entropy change of an ideal gas, what we're thinking about is the change in S with respect to V at constant T. This is an entropy change with respect to volume. And we don't know what that is, right? We don't have a good way of thinking about that. We don't have an equation for entropy of a van der Waals gas. But looking at this, this appears to involve some of these variables that showed up in our Maxwell relations. So if you go back and look at them, here is the partial of S with respect to V at constant T. And I know that is equal to the partial of P with respect to T at constant V. So if I go back and I look at that Maxwell relationship, it tells me that this happens to be a quantity that I can calculate really easily for a van der Waals gas. So remember, the equation looks like this: V minus NV minus A over N squared V squared. The partial of P with respect to T at constant V is equal to NR V minus NV. I can take and plug this in. Rearrange it. And I get an expression like that. And I'm going to stop here and I'll let you finish it and think about this. But you can see, or you can maybe start to see, that this will allow us to derive some quantitative relationships among thermodynamic quantities that become useful. All right, I'll stop here, and that brings us to the end of chapter 3. So we'll start talking about equilibrium after this one.